Okay, so today we're going to talk about sampling distributions. And we started to talk about this last time, but basically, usually our goal is that we want to describe some characteristic of a group of interest. And we quantify this through a population parameter. And that's what we are seeking to gain knowledge about, right, or to estimate. And so, as an example, we might be interested in the population mean or average, and that's unknown, right? That's why we have the question mark there. So our action is that we might collect data from a sample that's drawn from our population of interest. We would then calculate a sample statistic to estimate this population parameter. So if our goal is to estimate our population mean, we might collect data and then calculate the sample mean, which might be 6, right, in this example, because we know this. We collect data and that's our observed data, and we're able to actually calculate this sample statistic, and that's our best estimate of the population mean. However, the problem though is that the sample results that we get are partly a function of sampling error, and we'll talk about this more in a minute. But basically, it's this idea that if we collect data from multiple samples from the same population, even though they're coming from the same population, the results will vary from sample to sample. So the implication of this is, are our results from our sample informative about the population, or are they just reflective of sampling variability? In other words, how do we separate the signal from the noise? And so to make this more tangible, as an example, we might be interested in determining the average hours of sleep per night for U.S. college students. We might have a hypothesis that U.S. college students get 7 hours of sleep per night on average. So in statistical notation, we might write that our null hypothesis, our starting hypothesis, is that the population mean mu is equal to 7 hours. So we might collect sample data from 157 college students who happen to respond to a survey about their sleep habits. And then for our sample, the average number of hours of sleep per night for the students in our sample is 6.3 hours of sleep per night. So using our sample data, we calculate this sample statistic, which in this case is a sample average of 6.3 hours of sleep per night. And we denote that with X bar, which means that our sample average is 6.3 hours. But our problem, though, is that if we decide to repeat our study 3 more times, we might get different sample averages every time. So our first sample average, X bar sub 1, would be 6.3 hours. Our second sample average might be 5.2 hours. Our third sample average might be 9.2 hours, and then the fourth one might be 4.6 hours. And so these represent each time a sample that we are collecting and calculating this sample statistic, right? So it's a sample statistic that's still being calculated from samples drawn from the same population, but we're getting different results each time for our sample average. So the question is, if we only have access to one sample or a few samples, how do we know whether our result is actually meaningful? And when I say meaningful, I mean this in the sense of, how do we know whether or not this is actually reflective of a population parameter, right? Or a population trend or a characteristic. And so the way that we can help figure this out, or at least, make an educated guess, is we can use sampling distributions to determine what degree of sample to sample variability is reasonable. And so as a visual of this, our population might be right here, right? This represents the population of all college students, and our population parameter, our mean, the true underlying mean, might be an average of 7 hours of sleep for all college students on average. But then when we go to draw samples, our samples are subsets of our population. And so these different colors represent different samples, right? Our first one might be these red dots, right? So we draw these red observations and we get a sample average of 6.3 hours. But then if we were to draw another sample, that might be the green observations, and that sample mean might be 5.2. And then the third might be the blue, and we would get 9.2. And the fourth would be the yellow, and we might get 4.6 as our averages, right? And so the point being is that when we draw samples, the results that we get are reflective to some degree of the specific observations that we happen to draw from our population. And so at a conceptual level, when we talk about sampling distributions, imagine drawing samples of a certain size over and over from a given population. And for each sample that we draw, we calculate a sample statistic and we record its value. And that's just what we saw in that previous visual, right? We are drawing samples from the same population, right? In real life, we wouldn't do this often, but just conceptually, right, the sampling distribution, just imagine drawing samples from the same population over and over. And again, for each of those samples, we calculate a sample statistic and record its value. And those were our 4 sample averages in the visual that we just saw. Well, the distribution of these sample statistic values is our sampling distribution. That's all a sampling distribution is. So whenever you hear sampling distribution, for me, it helps to think instead distribution of sample statistics, right? That's all a sampling distribution is. It's all the values we might expect to get for a sample statistic if we sampled a bajillion times, right? So, as an example, if we drew an infinite number of samples from this population of all college students, and for each of those samples we calculate the average number of hours of sleep per night, the sampling distribution is comprised of all of those sample averages. And to help visualize this on a deeper level, I want to use this really cool applet. I'm going to post the link in the description. It's put on by Rice University, and again, the link will be in the description. And it's a really fantastic, simple way of visualizing what a sample distribution is. So what we see here at the top is our population, right? This is just our, hypothetical population of the average, the number of hours of sleep for all college students in the U.S., right? And so in this particular example, we see that the mean is 16, right? In our earlier example, we said 7, but let's just imagine it's 16 hours of sleep per night. Obviously, that's not realistic. But the point being is that this represents the distribution of the numbers of hours of sleep for all college students in the population. Okay? Well, to illustrate a sampling distribution, imagine that we draw a sample of 10 college students each time. So we administer a survey and we get 10 people to respond, and for each of these samples, right, we have them tell us the number of hours of sleep they get, and then we then calculate the sample average. So what this might look like is these are the 10 college students being drawn from the population for the first sample, and then this is the sample mean we might get. And so again, all we did was we just drew 10 observations from our population, which is equivalent to 10 people responding to the survey, and then we calculate the sample average, which would be our sample statistic. And then the next time we might do it again, and this time we get a different 10 observations, and then the sample mean we see down here again. This time it happened to be the same, just due to random chance. So if we do it a third time, this time we get a different sample mean. And so what we can see is that this is what the sampling distribution is. It's the distribution of the sample statistics, where if we were to sample from a population, and for each sample we calculate the sample statistic, and then we plot the distribution of those sample statistics, that's all it is. And so we could do this, over and over and over again. And so what I'm going to do is, instead of, showing each sample in real time, I'm going to skip ahead and just draw 10,000 samples. So what I'm about to do is to show you the results you would get if you did this 10,000 times, right? If we drew 10,000 samples and for each sample we calculated the sample mean, we're about to see what the distribution of sample means, or the sampling distribution, might look like. So I'm going to click 10,000, and this is how my sample means might be distributed. Okay, it's the distribution of sample means, or the sampling distribution for the mean. Those are all equivalent terms. And so what we see down here is that our sampling distribution has its own mean and its own characteristics, right? And so this is just a really powerful tool to show us how we might visualize what a sampling distribution is. And in this applet that's provided, you can even change the shape of your your parent population, right? So let's say I think that the population looks like this. Well, I can do the same thing. I can also change the number of observations in my sample, which will be important for a later video. But here I'm sampling 5 people each time and calculating the mean. Do it again. And then if I speed it up and did it 10,000 times, this is what it would look like. And the thing is that this applies for any sample statistic, right? It doesn't just have to be for the mean. We can do this for the median. And so I'm drawing drawing a sample of size 5 and calculating the median this time. And just like with the sample means, I can get a distribution of sample medians, right? We could do this for any of our sample statistics. And so this is all that a sampling distribution is. It's just conceptually what you would expect to see if you sampled from a population over and over and over again, and then plotted the sample statistics that you get. And so why do we care about this? Well, the main idea is that the sampling distribution, or the distribution of sample statistics, tells us what values are within reason for a sample that was drawn from a given population. So in the applet that we just looked at, we first, defined what we thought our population looked like, and then we were able to see how the sample statistics would be distributed for samples drawn from that population. So the sampling distribution tells us which sample statistic values we might reasonably expect to see when sampling from a certain population. And so the importance of this is that if we have a hypothesis about what we think the population characteristics are, so, for example, let's say we think the population has a mean of 7, for example, right? Like we've been doing. Well, the sampling distribution can help us determine what sample statistic values would be within reason. So the sampling distribution for the mean would show us what type of sample means we might expect to see if we drew samples over and over and over from a population with a true mean of 7. And if we only have a single sample and sample statistic, we can compare that sample statistic that we've calculated to the sampling distribution, and this can tell us the probability of getting a value like the one we got if this sample really came from this population that we think of. And I know that's kind of an awkward phrasing, but again, the idea here is that if we draw samples if we draw a sample and we calculate our single sample statistic, right, the sampling distribution can tell us basically the likelihood that our sample came from this population, because it tells us the probability of getting the sample statistic value that we really did get if our sample had really came from this population, right? So as an example, in our instance, where our hypothesized population mean for the average numbers of hours of sleep for college students was 7, well, if we get a sample average of 6.3, if we just draw one sample and get a sample average of 6.3 hours of sleep per night, we can compare this sample average of 6.3 hours to the distribution of sample means for a population where the true mean is 7. And so what we might see in this hypothetical example is that 95% of the sample means are expected to fall between 6.5 hours and 7.5 hours. And because our actual sample average was 6.3 hours of sleep, it falls outside of this 95% interval, right? And so this might be an example of how we could determine that there's only a very low probability of getting a sample mean or sample average that's as far away from the population mean as ours if our sample really came from this population. So I'll say that again, right? If the population mean really was 7 hours of sleep per night, well, the sampling distribution, or the distribution of sample means, can help us determine what percent of the time, if you were to draw samples over and over and over again, you would expect to get a sample average that falls at or below the average that we actually got, right? And so we can determine the likelihood that our sample really did come from a population that has this characteristic, this hypothesized population parameter, which for us was a mean of 7. And so sampling distributions provide us a way of determining the likelihood that our sample really did come from a population with a hypothesized characteristic, right? And so we now understand why sampling distributions are useful, but how do we calculate them? We can't really just draw samples over and over and over and over again and calculate an infinite number of sample statistics from every single population that we're interested in. But luckily for us, statistical theory tells us about the expected characteristics of various sampling distributions under certain conditions. In other words, statistical theory tells us about the characteristics we might expect to see for a distribution of sample statistics under certain conditions. And so the next video is going to talk about one critical theory, and that is the central limit theorem. Thanks for watching, and the link to that applet is in the description. And thanks for watching the video.